All right, so let's tackle this test. I mean, it's more of a quiz than anything. There's really just 4 questions on here, but I think they're worthy questions with regards to kind of dynamics, which is really all about forces. So part 1 of the test, which covers a certain number of items related to forces. I'll put up a link up above there. So this is part number 2. And as I normally do with these particular tests or quizzes, I will put the link in the show notes or in the description so you can download it for yourself, so you can have this test and then give it a go. And then once you do give it a go and you try to solve it, so give yourself maybe 40 minutes or so, and then you can come back, okay, and then watch the solutions to see, how well you have done. All right, so let's get started. So first of all, again, so rounding, so round your significant figures. Well, most of the time in physics, if you're not told what to round to, you should kind of keep the same number of significant figures as the measurement with the lowest number of significant figures, right? And try not to round in intermediate steps, right? So that's what I'll try to do. So here's question number 1. Okay, so this is a pretty neat question. It's actually a very realistic question. Okay, it's with regards to the moon going around the Earth, and so you can see how the actual forces and accelerations play a role here. So the moon has a mass, and it's it's rather big. Okay, as you can see there. So here's the mass of the moon. So that's one. The Earth has a mass. So if we're told these 2 pieces of information. The distance between the centers of the moon and the Earth is also given to us. So if you were writing this out for yourself, okay, let's say in terms of givens, you can draw this out. It's always useful to be able to do that. So if you have, so let's imagine this is the Earth. So the moon is going to be smaller. So it's about a 1/6 smaller or so. Okay, so let's say that's the moon, that's the Earth. And now, so they give us what the masses are. So here's the mass. Okay, I'm going to call this mass number 1. And this particular mass is 7.34767 times 10 to the 22. So this is where your scientific notation comes into play. Your mass number 2, which is of the Earth itself, is going to be 5.97219, and notice the exponent is much bigger, so it's 24 instead of 22, and this is why the Earth is actually bigger there. Now both of these are in kilograms, which is exactly what we want because that is the metric SI standard unit for mass. Now it also tells us that the distance between, so this is the distance between the 2 centers. So if you would be measuring this particular distance, okay, so let's imagine, okay, so this is the centers. Now that distance, you can call it D, you can call it R, okay, so whatever it is that you like. I typically try to use R, but I have used D as well. So this is the radius. Now the radius is 3.85 times 10 to the 5 kilometers. Now, so this is kind of, notice it says kilometers. That's not what we want because that's not the SI standard in our formulas. So I'm going to change this. Now, changing it from kilometers to meters is rather easy because you're just going to be multiplying it by 1,000 because there's 1,000 meters in every kilometer. So this would change this to now, instead of having 10 to the 5, it would have been 10 to the 8. And now you can have meters, again, your SI standard. So that's what we have as a given. Now, what else are they asking us here? So for part A, and this is what I'm going to try to do first. So in part A, it says, what is the speed that the moon is moving at around the Earth? So indeed, it is true. And this is what we observe and we can see. So this, moon, so it's kind of shifting around and it kind of goes around the Earth, okay, and then it comes back, and it's, so here's, I'm trying to do it in 3D, but it's kind of a more or less a circular motion that you have. And so what that means is if it's moving at a particular speed, and indeed that's what happens, you may recall that there's going to be 2 things that are kind of at play. Well, first of all, between any 2 objects, we know what the force that is present there, right, between any two objects. Now, in this case, we're talking about the moon and the Earth itself. So what is the force between them? So that's something that we can certainly calculate. Now, that particular force, okay, between those is the force that is keeping, okay, that's kind of the centripetal force, okay, which is the force of the gravitational pull between the two objects. Okay, so those are going to be equal. So let's keep that in mind. So that means the centripetal force, so centripetal, so C or CE, is equal to the same, okay, so this is going to be of the gravitational pull between, so that's what must be keeping it in, okay, kind of in orbit in there around the Earth, and that is equal to, okay, so we have two kind of equations in here. So let's, write that out in here. So I'm going to write this out. So the centripetal force that I have in here is going to be the mass. Now we're talking about the moon, so I'm going to put mass number 1, okay, in here, times the speed, okay, of the moon, okay, that it's going at, and that's going to be v squared, and that's going to be divided by r, and that is the radius, okay, of the actual circle, more or less, that it makes. So in this case, the radius is actually the distance between the centers of the Earth and the moon. Now, on the other side, the gravitational pull that this must be equal to, that's actually keeping it in orbit there, is going to be, so it's going to be capital G, multiplied by the two masses, so M1, M2, divided by your radius, or the distance between them, okay, squared. Now, since I'm using r as the radius, I'll keep r in here as well. So they must be equal to each other in order for the moon to be kind of going around. Now, notice they're asking us for the velocity, right? So this, okay, this is going to be a constant velocity, right? So that this is moving at. Now, depending on how you're looking at it, like in which rotation is it moving. So that velocity is what we want. Now, we have all of the given pieces of information. So you can go ahead and substitute everything back in, and you will get what your velocity is. So we can certainly solve for that. So I'm going to just shift this over, okay, over here. Now, I do notice, actually, so if I rearrange this, so notice what I'm going to get is I'm going to get v squared. It is going to be equal to, I'm going to have my capital G in there. Now, notice that M1 and M1, so that's going to cancel the actual mass of the moon itself, right? So it's only going to leave the mass of the Earth, so that's mass number 2, okay, that you have in there. Now, the other component, notice that you have an r and you have an r squared on the other side. So if you bring this particular r over, so this r, if you multiply both sides by r, so if you would do this, okay, then obviously this would cancel, and this would cancel one of these. So what you're going to have is, in the denominator, right there, you're only going to have one r, because one of the r's will cancel. So that's all nice. So that means here is we have our G, we have our M2, the R, okay, and then the R squared, so that's all gone. And now you can see that V is going to be just the square root, okay, of all of this junk. So whatever this is. And now we can substitute this back in here and find out. Now, you didn't have to rearrange this formula. You could have just substituted it all in. You could have found what the gravitational force is on the right-hand side, and then you could have just divided by the mass of the moon and then multiplied by the radius, and you would have gotten the same thing, and you could have taken the square root. So now I'm going to take out my calculator in here. I'm going to plug everything back in. So capital G, so you may recall, so this is just 6.67 times 10 to the negative 11. So that's what this is. So that's what I have there. Now, this is going to be multiplied by, so I'm going to multiply it by the mass of the Earth. So I'm going to take that and maybe put that in. So 5.97219, right? So times 10 to the, and this is going to be 24. So you have that, so that's multiplied the capital G, and now I'm going to divide. So all of this is going to be divided by, I'm putting it all in brackets here, by the actual radius. So it's going to be 3.85 multiplied by 10 to the 8, and that will give us what the answer is, okay, right there. Now I have to take the square root of this, right? So whatever the square root might be in here. So I'm going to take this answer, okay, taking the square root, so within here, so it's like taking a fraction of the exponent, which is 0.5. So that's the same thing, but you can certainly use the square root button, and that's going to give us my answer, okay, right there. So which is really fast. As you can see there, it's 1017, you know, etc. I'm not going to write out more, but this is meters per second, which is really quick. So if you would have changed this to kilometers per hour, so this is going to be approximately, if you wanted to change the units, not that it asks us to do that, but it's going to be approximately 3,600, a little bit more than that, kilometers per hour, which is, as you know, that's really, really quick. So the moon is actually spinning around, or the Earth, rather quickly. It just doesn't look like that because of the fact that it's just so far away, and the distance that it covers relative to the entire rotation, okay, is rather large. So that is my actual speed. Now, because of the fact that we want to be able to round to the significant figures, so I have 3 is the maximum in here. So I'm going to do that. So this is going to be rounded to, so you can round this up, okay, and it's going to be 1020 meters per second, okay, and that would have been the velocity, right? And that's perpendicular, right, to the actual circle that it's made. Now, what else does it ask us in here? I'm going to move that out of the way. Calculate the centripetal acceleration of the moon. Okay, well, for centripetal acceleration, so if I wanted to do that, so that would have been B. So this one is actually rather easier. So this is just V squared all over R, right? We don't need the mass or anything of that nature, so we can just take this. Now, since I already have this on the calculator, so I can take this even without rounding in here. I can square it. So I'm going to get my answer over here. And now I'm going to take my answer and then just divide it by, so this is going to be divided by R, which is going to be 3, sorry, I'm going to rewrite this, put it in brackets, 3.85 times 10 to the 8. And of course, this is going to be a smaller acceleration. So this is, and let's put this up in here. So 2 point approximately, 69 times 10 to the 1 to negative 3. This is meters per second squared. And that's what you would have had. Now, I would encourage you, you can take up and look up on the internet what is the actual speed, right, that you are moving at. And just to double check, okay, to see, if we've actually done our calculations. We should be rather close. Of course, we might be off a little bit on the rounding side, but that's what we should have in meters per second, and approximately, 3,600, a little bit more than that, kilometers an hour, if that's what you wanted. So that's question 1. So this was a really nice question with regards to combining, Newton's gravitational force with the centripetal force as well, and then calculating centripetal accelerations. Okay, here is question number 2. So here we have a cyclist. This cyclist has taken a turn, has a radius of 12 meters. So I'm not going to try to draw the cyclist, but I'll try to draw a box. Okay, kind of like a free body diagram in here. Okay, so it's taking a turn. So let's imagine, we're kind of going around in here. So here's the radius right there. So that radius, it's telling us, is 12 meters. Okay, so that's my cyclist there. That's what I have. The cyclist has a mass. So we have a mass. So this is my given pieces of information. So this is 62 kilograms. The bike has a negligible mass, and I guess it's true nowadays. I mean, really good, nice bikes don't really weigh that much, although I don't know if it would have been super negligible, but that's what it says in the question. The speed the cyclist is moving at is, okay, so they're moving at, so this is V, and that's going to be 21.2, and this is kilometers per hour. Well, that's not what we like. Okay, this one is in meters, this one is in kilograms, so that's all in nice SI units, but kilometers per hour, okay, so that's not a standard unit. So it's certainly a metric unit, but it's not a standard unit. So we can change this up. So let's do that rather quickly. So 21.2 kilometers per hour. So if I do the conversion, So you may or may not remember. Let's get rid of the kilometers. So we know that 1 kilometer is just simply 1,000 meters. And then we have 1 hour, okay, is equal to 60 minutes. Okay, and so let me just shift this over so I have space there. And then you have that 1 minute is equal to 60 seconds. All right, so now you can substitute all of that in, and so that's going to be 21.2. And really, okay, so what you have is this entire thing. So I mean, I kind of memorized this. It's going to be divided by 3.6. Okay, in there. So that's approximately, 8. I'll leave those 8s in there. This is meters per second. All right, so we're going to use that, I hope. Okay, let's see what they ask us. Now, part A, what is the centripetal force around the curve? Okay, so if we want to know what the centripetal force is here, well, the centripetal force is equal to the mass, V squared all over R. So that's not very difficult. So 62, and then, so this is going to be 5.8, okay, squared all over the radius, which is 12. So we can get what the, now since I have this on the calculator, I'm going to take this and square it, all right, right away, so I don't have to rewrite anything. So that's going to be V squared. Now V squared answer, so times 62, which is the mass, and then divided by the 12, all right, which gives us 179 newtons. Now to, let's see, to 2 significant figures, which is the lowest one, which would have been 180. All right, so this is approximately 180 newtons, and that is, of course, towards, right? So this is, okay, so if you're thinking about this, this is kind of going in this direction, right? So it's going towards the center. That's your FC. Now, in here, it also asks us, so notice, what is providing the force during the turn? This is always a great question. And to be honest with you, when I was in your shoes, probably, starting this off in physics, I always had a kind of a hard time thinking about this. But you may recall, so if you're riding anything, this is if it's a car, if it's a bike, whatever it might be, if this force is in this direction, that centripetal force is keeping you in that, turn, so there has to be, from Newton's third law, so actions and reactions, like where is it coming from? It is actually coming, so here, maybe I'll do it in a different color. Okay, so there has to be, it's almost like you're pushing on the ground in this direction, right? And that first, so this is the actual, push that you have there, okay? The tires, pushing against the ground in there. And then this rebound, okay, which is that centripetal force that you have. In the previous question, we saw that it's coming from the gravitational pull, right? But in here, it is actually coming from the friction, the static friction that doesn't allow the tires to skid away, right? So the tires are pushing against the ground and the ground pushes back, and that pushback causes that centripetal force, okay, to keep it in that turn. And if that, is not going to be strong enough, that cyclist is going to be skidding away. So anyway, so where's it coming from? It's coming really from the static friction between the tires, okay, and the pavement. So that's what you have there. Now for part B, if the coefficient of static friction between the tires and the pavement is 0.62, then will the cyclist make the turn or skid out? Okay, so now what does this mean? So what it means is if you're going to be pushing in here, right, and so this is going to be your friction, okay, that is pushing back, which is really the centripetal force, okay, that's where that is coming from. Then what you have, so this is for part B, okay, so that static friction, S or F, we want to be able to find out what the maximum is so it doesn't skid away, right? Now, where does this come from? Well, this comes from, okay, your coefficient of friction, which is always equal to, okay, so for static friction, it is the maximum divided by the force of normal, right, that you have. So in other ways, okay, so this is going to be nothing else but the static friction times the force of normal. Now we are told that it's 0.62. So that's that. My force of normal in this case, it doesn't really tell us anything So we'll just assume, okay, that it's the force of gravity, right? So what you have is, okay, within here, so as this cyclist goes, you have your force of gravity down, and then you have your force of normal up, and these are going to be equal to each other, so long as there aren't any angles or anything like that. So this one would be, so the mass was 62 times 9.8. So let's see what this is. So 0.62 times 62 times 9.8. Okay, so that is about 376.7. Well, to two significant figures, it's about 380 newtons. Now, significant figures or not, so you can see here that this maximum, right, is definitely bigger, right, than which is what we need. And what happens is that means that this actual cyclist is not going to skid away because the force of friction is big enough. You would need to exceed this force of friction when it no longer can keep those tires in static, right, and just kind of let them, then they would start skidding away. And then you have kinetic friction as it skids away on that surface. And that's always a worry. Now, of course, this is actually a pretty large coefficient of friction. If you have a wet surface, you've got to be careful how you take those turns because this thing actually does come down. And it will depend on the tires that you have as well. And when it comes down, you have to sometimes slow down. I certainly have taken a wipeout where I've unfortunately was in a pretty bad accident on a cycling in the rain, and my tires did skid out. In any case, so this indeed is enough. Okay, so will you skid out? No, you will not. Here is question number 3. So let's take a look at this. So a 225 kilogram object is sliding at a speed of 3.5 meters per second to the right. Okay, so again, I like these free body diagrams, so let's utilize them. So you are moving to the right, and you're moving at a speed of 3.5 meters per second. Now, this object is 225 kilograms, so that's all in standard units. This is in standard units. A constant force of 95 newtons to the left is applied. We don't know where this is coming from, but in any case, so we have a force. This is of 95 newtons. It's applied until the object stops moving. So basically, something is trying to prevent this from moving. The coefficient of kinetic friction is 0.18. Okay, well, if there's kinetic friction, which kinetic friction always opposes the motion, so if the motion is to the right, so that means that the kinetic friction is going to be to the left. Now, I don't know if it's bigger or smaller than the 95 newtons, but we'll calculate it. I think it's going to be bigger, probably by a bit. But in any case, so that doesn't matter. I'm just going to put Fk, and I know that it's in the opposite direction. And so this, as you saw from the previous, is going to be your coefficient of friction times Fn. So this we can actually calculate. So this is going to be 0.18. And then your force of normal, so force of gravity is down, force of normal is up. You can put that in your free body diagram. And this is a rather big item in here. So that force of normal is going to be big. Let's see what this is. So I'm going to just put 0.18 times 225 times 9.8. So this is 396.9. I'm not going to do any rounding here. This is an intermediate step. Okay, so it is bigger. It's about 4 times bigger. So that arrow, obviously this is should be going off there quite a bit. Okay, or you can make this one smaller so that it looks kind of like a 4th. Not that it matters, right? I mean, just hopefully your teachers are not that picky. As long as you're kind of drawing it in the right directions and then you're labeling them, it should be fine. So what is the distance traveled by the object before it stops? Okay, well, I mean, it is moving. So, and then there is a force here. Well, there's 2 forces. So it definitely will decelerate the object to a stop. Okay, so what does that mean? Okay, so with this in mind, so now what we're going to have is that our net force let's assume to the right is positive, is going to be equal to the mass times the acceleration, which equals to the summation of all of the forces. Now there are two forces, but both of them are in the opposite direction here. So I'm going to put a minus. This is 396.9, so both of them are minus, and the minus will just tell us that we're decelerating in this case. So my acceleration is equal to, so whatever you have over here, so let's see what that is. So it's going to be negative 95 minus, this is 396.9. So that is the total, so negative 491.9 divided by the mass, which is 225. So answer divided by 225, that will now give us that the acceleration, is so negative 2.1806, and then a bunch of 2's in there. So that's what we have right there. All right, so I'm gonna keep it on the calculator in case I need it. So now that we have the acceleration, now why would I need that? Well, they're asking me what's the distance before it stops. So you can do one of two things. If you have your acceleration, now please don't forget that your V final is 0, right? Your V initial was 3.5 meters per second. Okay, so that's what you would have. So now by the definition, so your acceleration, your average acceleration throughout would have been the change in V over the change in the time. So you can certainly find out what the time is that it took, and then you can substitute it into the distance equation, your accelerations, your initial, your time, and then you'll have it. So that's one way to be able to do that. If you've done that, great. Now I'm going to kind of recall one of the formulas in kind of kinetic motion when you don't have the time is this one. So it is your final squared. Now this only deals with magnitudes, which is your initial plus, which is going to be 2 times the acceleration, so whatever average acceleration times the distance that you've covered. Now this equation is nice when you don't have delta t directly. Now I'll put up a link up above there to the kinetic equations, kind of all of the ones that you have if you've forgotten this, but this is one of them. Now why I'm putting this in here, because I have all of this. This is 0, right? Because it's final, we're stopping. This is 3.5 plus 2, and so it's going to be negative 2.186, etc. in here, 2, and then I can solve for delta d. So I can solve all of this for delta d. Okay, so let's see, this I can move to the other side. So that's going to be negative, but then the other negative is going to cancel. So I'm going to have my delta d. So my delta d is going to be equal to, I'm going to go back in here. So this is squared. Okay, so this is going to be 12.25. So that's the negative divided by, and then it's going to be all of this junk, 2.186. Okay, and that's your delta d. So so the negatives cancel, that's gone. So my answer divided by, now let's do that, 2 times 2.186, whatever, 2's in there. And this is what we would have right there. So this now equals, 2.8. Now I will round. And this is going to be meters. So that's how many meters it would slide before it would actually stop. All right, so that's what you would have in there. Now let's double check, make sure everything is okay. All right, so this is my force, okay, of friction. So that's opposing it. So we found our acceleration. This was utilizing the actual mass in there. So this is what we had right there. And then we substituted this back into here. We substituted our initial, and then we solved, well, VF was 0. So then we solved for D. So there you have it. So that's actually a great question here. There's nothing else. All right. Okay, so here's the last example. So in the previous example, if the object stops and has a static friction coefficient, so if it stops moving, now the static coefficient is 0.42. relative to the surface. Well, then what is the minimum amount of force needed to get the object to move? Okay, well, in order to make it move, you have to overcome. So let's imagine, you know, that you're trying to push this in this direction. So that means you're going to have to overcome the static friction right there, which is going to be opposing you. And that static friction, so this is going to, you have to overcome the maximum static friction, which is this times your force of normal, right? So your force of normal is obviously up, you know, your force of gravity is down. I'm going to actually remove this. So if you substitute this back in here, so 0.42, force of normal, 225 times 9.8. Let's see how big this force would have to be. 0.42. Notice the static one is bigger than the kinetic one. So 225 times 9.8. Okay, well, that's a lot of force. If it's 2 sig fig, so this is around 930. Now, this force, this is the minimum, right? This would still keep it static, right? So this is still a force that you would have to overcome. So it has to be greater than this. Okay, so whatever you pull, it has to be greater than this. So it has to be, okay, greater. So the force applied, so this force applied has to be greater than this. Okay, well, if you've rounded to 2 sig figs, well, 230 is going to be greater. So that's what you would need to get it to accelerate again, right? To get it to move. Now, it also asks us what is the minimum amount of force to keep it moving at a constant speed. So indeed, so once you do get it to move, now it's in motion. So it's no longer static friction that plays a role. Now it's going to be kinetic friction. Let's call this A. Let's call this B. So for kinetic friction, so what you will need, because you're going to have to basically overcome, right? So to keep it moving at a constant speed, so whatever you apply has to balance off the kinetic friction that you have if there's nothing else. And I'm assuming there'll be nothing else. They don't mention anything. Air resistance would be negligible. But so this is the kinetic friction. This is the applied. And now this one will be, now let's go back to the previous example. It was 0.18. All right, so this is going to be 0.18. So that's what you have to overcome. So 225, you know, times 9.8, okay? And we've actually calculated this in here. That was 396.9, right? So let's just do it again. 0.18 times 225. Oh my gosh, I hope I didn't get it wrong last time. All right, so 396.9 newtons, or, you know, 300. Oh, well, if I'm rounding to 2 sig figs, oh, this is interesting because it's going to be 400 newtons. So if you want to write it to 2 sig figs, put it in scientific notation. 2, well, notice 2 sig figs right there, because if you just write 400, that would seem like it's only 1 sig fig. Anyways, I don't think your teacher will be that strict, but you know, if he or she is that strict, then you know, maybe you'll only lose a little bit. But in any case, this would have been the answer. That's how much force. Obviously, it's less than the static one in this case because the coefficient is much smaller. All right, so that is it. Okay, so this is a really nice test or a quiz with 4 questions related to really centripetal acceleration, centripetal force, gravitational forces from Newton's law of gravity, and it also has static and kinetic frictions. Okay, thanks for watching. See you in a future video. Bye, everybody.